Hey guys, welcome back. Today we will discuss about one of the widely used object detector in the whole object detection family, that is YoloV4. YoloV4 is very popular and it is widely used in the whole industry. Even though newer versions came like YoloV5, V6, V7 and recently V8 also has been released, because of the license issues, most of the people in the industry prefer YoloV4. Beyond YoloV4, from YoloV5, the license has been changed to GPL3, which is actually restriction for commercial purposes. So the YoloV4 to V8, all these models are only specified for research purposes. That is one of the reasons YoloV4 is still widely used. We saw YoloV3, which is just a small improvement over YoloV2. But no one in the research community expected the next version of YOLO to be released, because one of the author, Joseph Redmond, he actually decided to stop the CV research because of the ethical issues. Because he saw that it has been used in the military applications, and because of ethical issues, he doesn't want to continue the YOLO series. But someone had to continue the journey because YOLO object detection models were very popular and they are actually the go-to models for most of the real-time applications. So the same work has been extended by another guy named Alexei. So you might have known him as Alexei AB. You might have seen the GitHub repositories. The YoloV4, scaled YoloV4, all these are actually implemented by him. So the extension from YoloV3 to V4 has been done by Alexei AB. So enough with the introductions. Let us understand YoloV4. As I mentioned, YoloV4 is the go-to object detector, the best object detector at that time, because it has both speed and accuracy. In fact, the title itself says it has optimal speed and accuracy. There might be so many papers published saying that they are the state of the art in the COCO object detection or some other open images or some other like that. But they might be very complex models which are not fitting in the real-time applications. But YOLO here is actually having an optimal balance between the speed and accuracy, which makes it a good fit for the real-time actual deployment. So you cannot simply do the research and keep on increasing the accuracy. Those are good for publishing papers. But how much of them are actually used in the deployment? In fact, the older YOLO versions also, the moment YOLO object detection series has started, YOLO version 1, version 2, version 3 and now version 4, all the along the way, whenever a new version got released, that is very quickly and rapidly adopted by the industry because they are actually very fit for the real-time applications. Now let us see what they mean by this optimal speed and accuracy. Before going any details into the architecture and the mechanisms they have used, we will just look at the results. Why they say that this model has the optimal speed and accuracy. So these are the results. So you can see there has been many conflicts between whether to use AP average precision or average precision 50 for actually comparing the different models. But anyway, if you compare both the charts, we will just keep that conflict aside and we will compare both the charts here. If you observe YoloV4 and YoloV3, YoloV3 here is the older one. If you compare this, so it is almost giving 70 plus FPS, right? And the MAP is almost like 33. These are actually the best models because these are having the highest MAP. So for the same FPS, it is actually giving 43. So you can see almost 10 MAP jump between YoloV3 and V4 for the same speed. And if you compare the fastest models also, YoloV4 is slightly faster and this is also having almost 10 MAP difference. So having 10 MAP difference is a very big thing in the object detection. And this is achieved by YoloV4 and keeping the FPS almost same as YoloV3. In fact, it's slightly better than YoloV3. But if you check the state of the art, you can see that efficient det is actually the state of the art model. You can see that in COCO MAP, it is almost reaching 49 point something, almost reaching 50. Whereas here, YOLO has stopped at 43 point something. If you see, almost like 6 MAP difference is there. But still, if you check the FPS, the speed wise, it is actually almost taking around 12 or 13 FPS like that. So having a 10 FPS model is not feasible for real-time applications. Even though the MAP is higher here, but the FPS is still low. And if you compare the same FPS where YOLO is starting the 60 plus FPS, if you compare that, the MAP of the efficient det is 34. It is still lesser than YoloV4. So that way if you check, YoloV4 is having an MAP which is reasonably well, and at the same time it has having the FPS of 65 to 70, even the best model, which is a very good speed in terms of real-time applications. So that is the reason YoloV4 is very widely adopted by the industry. Even till date, YoloV4 is the most used object detector. So how did they achieve this MAP jump keeping the same FPS as YoloV3? Right, we are considering this as an improvement on top of YoloV3. It has a lot of references taken from multiple papers. A lot of techniques have been adopted in the YoloV4 model to achieve this accuracy and at the same time maintaining high FPS. A generic typical object detector consists of these components. So backbone is for extracting the features, and there are many choices here. For backbone you have VGG in the beginning, older models, and the same time ResNet, DenseNet, MobileNet. So these are all the different options for backbone. At the same time, the backbone is followed by neck. Neck is actually used for enhancing the features or aggregating the features. So there are two purposes. So some type of neck actually are used for enhancing the features. Like you can see SPP, spatial pyramid pooling. These are actually used for enhancing the features. At the same time, FPN or PAN, all these models are actually feature aggregators. Aggregators in the sense, when the backbone is generating the features from the given image, it generates the features at different layers. So now these different layers outputs are actually aggregated in a better way to have optimal features or best features for going to the head for the predictions. So that is what this neck part will do. So in the older models, there is no neck actually. In fact, the faster RCN or the YOLO version 1, version 2, they don't have neck. They have only backbone part and then passing the features coming from backbone directly to head, detection head. So coming to the detection head is actually where your object detection, bounding box predictions as well as the class predictions are happening here. So for the head part, there are two types of networks. One is single stage detectors and second one is two stage detectors. Of course, YOLO belongs to single stage detectors, whereas two stage detectors are mask RCNN, fast RCNN. These are all RCNN based approaches are two stage detectors. So the prediction head, we actually do dense prediction in single stage, whereas for two stage, we do sparse prediction. So these are typical components for an object detector. Now we need to see in YoloV4 which of these components are adopted, because we saw that in backbone there are many options, for neck there are many options, and for head there are many options. We can take any of these. So which of these are actually finalized for YoloV4, we will see that. So these are the finalized modules at each stage for YoloV4. The backbone used in YoloV4 is CSP Darknet. Darknet is used in YoloV3. It is the same Darknet model, Darknet 53, which was used in YoloV3. Same model, they have actually modified and then created a new network called CSP Darknet. That is used as the backbone. And then on top of it, SPP is used as a neck for extracting better features from the existing features from backbone. And then that SPP features which we are getting, those are actually aggregated at multiple stages by path aggregation network, PAN. Now this path aggregation network is used for the neck part. Now once we got the features at different levels here like this, and all these levels, predictions are made on the detection head. So now for the detection head, the same as YoloV3, whatever the YoloV3 detection head is there, the same thing is used at this stage. There is not much modification in the detection head in YoloV4. So these are the modules which they have added from the architecture side. So whatever we have discussed so far is from the architecture side. But apart from the architecture side, they have adopted so many modules. You can say from the training perspective, training mechanism perspectives, or inference perspectives, or you can say some kind of generalization, regularization activities, and from the data side, the augmentation techniques. So like this, many techniques are adopted from different papers, and they have actually used in an optimal way in the YoloV4. Overall, YoloV4 looks like this. So input image is passed to the backbone. It has many pyramidal layers, and after that it is passed through the neck, which is actually path aggregation and spatial pyramid pooling, and then at different stages, the features are actually passed through modules, this one. So these grids actually indicates feature maps at different scales. Okay. And then your detection head is same as YoloV3. So you have still bounding box predictions, which are offset of 4 values. And this is objectness score. And these are class probabilities, which are used in the final boxes here. So this is how the final boxes will come. Now these final boxes, we actually, one thing is thresholding we will do, because greater than 0.5, at least the confidence score should be greater than 0.5 to consider it as a final prediction. That is one thing. Along with that, for the overlapping boxes, we use non-maximum suppression for removing the overlapping boxes. And then finally, we get this kind of prediction. So this is the overall structure of YoloV4. Now, as I was mentioning, what are the other things which are considered in the YoloV4 repository? We are not talking about the architecture. We are talking about the repository perspective. So includes architecture, at the same time training mechanisms, testing mechanisms, data argumentations, all those things. The performance optimizations they have done is broadly divided into two categories. One is bag of freebies and one is bag of specials. Bag of freebies is actually kind of not increasing the complexity of the model, but during the training time or from the data side, whatever modifications we can make to improve the accuracy. But from the architecture side, we don't do too much of modifications so that the complexity remains same. Whereas bag of specials can have modules which can increase the complexity. For bag of freebies, different optimization methods are used during the training as well as inference, but these doesn't increase the inference time. Inference time still remains the same, but it might increase the training time. This one of the reason might be argumentations, right? So the data argumentations, when you add more data using argumentations, your training time will increase, but your inference time will not be impacted. So those kind of techniques are actually bag of freebies. Whereas bag of specials is actually some kind of modules which can improve the accuracy, but at the same time it can increase the inference time also, but it is very minor increment. So these are the broadly two categories they have done. One without increasing the inference time, and the second one with a small increase in inference time which can improve the accuracy drastically. These are the methods which are used in bag of freebies and bag of specials. As I mentioned earlier, bag of freebies has to do more with the training time mechanisms which might increase the training time, but the inference speed will be the same. So these you can see that in the backbone part and at the same time in the detection head, what are the things used in bag of freebies? Mostly from the backbone side or from the data side, these are the augmentations, cut, mix and mosaic augmentations. So we will go in detail about these things in the coming videos, but you can see that these cut, mix and mosaic are data augmentation methods. So like given an image, you generate 4 images, 10 images from a single image. So that kind of augmentations. So whereas mosaic is actually combining 4 or 8 grid kind of images in the grid fashion into a single image so that you create images at different scales. So these kind of augmentations are used in the training time, which is one of the reason the training time has increased. At the same time, drop block. So you might have heard about dropout, randomly eliminating some of the neurons in the model. Similar way here, drop block is used. Instead of dropout, drop block is used. At the same time, label smoothing. So you might have seen the labels. Usually we use 1-hot encoding vectors. So 1, 0, 0. This is the label target we use usually, right? If this is my target class, that will be 1 and others will be zeros. Whereas in case of label smoothing, instead of this, what we use is 0.9. Okay, 0, 0, 0. Instead of one hard value, we actually smooth the labels by some value, particular values, right? 0.9 like that. In some cases, you might increase this 0 to 0.1 or 0.005. And then from the detection side, the losses, they have added IOU loss. You have the regression loss, you have the classification loss. Along with that, they have added IOU loss. And also they have added batch normalization. They modified the batch normalization with the cross mini batch normalization. And drop block is used in the detection part also, not only in the backbone. Mosaic augmentation, we have already seen this. And then there is one more concept called adversarial training. Adversarial training is kind of making the model robust to any kind of hacking or something. So this is a completely different field. Self-adversarial networks is actually a completely different field altogether. But during the training itself, you can adopt one of these methods to make the model robust to any of these variations. So we can see in detail about these things in the next videos. And then they have used multiple anchor boxes for the single ground truth, and then learning rate scheduler. So when you are training, usually learning rate is used, LR, which is initialized with 0.001 or 0.0001 like this for Adam optimizer or SGD optimizer. So that learning rate should not be staying the same value during the whole training process. It should be modifying the values according to how the loss values or how the validation accuracy, all these parameters changes. So there is one kind of scheduler, cosine annealing scheduler. So that learning rate scheduler is used. So there are multiple learning rate schedulers like step learning rate scheduler, plateau based schedulers like that. So similarly, cosine annealing is one of the scheduler. So that is learning rate scheduler. And for getting the hyperparameters, usually hyperparameters are these only, like learning rates and anchor points. All these values are hyperparameters. These hyperparameters usually we decide ourselves based on the dataset we have. But here they have proposed a genetic algorithm for actually getting the optimal hyperparameters. So for getting the optimal hyperparameters or the anchor points, which anchor boxes usually are optimal. So they actually run a sample on the dataset we provide and they come up with the optimal hyperparameters, right? So these are evolution algorithms they have used, genetic algorithms for getting the optimal hyperparameters. Automatically the learning algorithm will get the hyperparameters. At the same time, training at random training shapes. So instead of fixing a particular scale and then training only on that scale, the training you can do on multiple scales to handle more variations in the dataset. So that is one thing. So these are all mostly with respect to the training mechanisms and the data part. This doesn't increase the complexity of the model. At the same time, this doesn't increase the inference time. Whereas BoF specials is actually modules wise a little bit changes to the architecture, which might increase the complexity of the architecture. At the same time, the accuracy will be very high. So this mesh activation, usually we saw ReLU activation and sigmoid, these kind of activations. In fact, we discussed about mesh activation in one of our video series, activation function series. You can check that actually. But mesh activation is one of the latest activation function, and it is proved that it is more robust compared to ReLU and leaky ReLU activations. So this is actually adopted in YoloV4. And cross-stage partial networks. So this is used in CSP darknet. We have seen earlier, right? So darknet has been modified to CSP darknet. So in the backbone part, they have added this module called cross-stage partial connections, which has actually improved the model accuracy. And also this particular thing has an ability to reduce the complexity also. We will discuss more detail. And then we have multi-input residual connections. So this is also used in the backbone part. So these are the activation, these are the mechanisms used in the backbone. At the same time, in the detection part, once the backbone is done, you have neck part and detector part. So in that neck and detector also, mesh activation is used. SPP block, spatial pyramid pooling. So that is used in the neck part. At the same time, attention mechanisms. So this SAM is actually spatial attention mechanism. So attention mechanism is used to actually attract or to eliminate less important features and to boost the more important features. So that attention mechanism we will see in detail. And path aggregation network is used in the neck part. At the same time, instead of using normal NMS, it has used DIOU NMS for the post-processing stage, okay, for filtering the boxes. So these are different techniques adopted in YoloV4, which is giving the boost in the accuracy, keeping the speed at the highest. Okay, usually when one is going up, the second one goes down. Usually for any of the object detection or any of the classification models also, as the accuracy increases, that means the model is becoming more complex. So it automatically reduces the inference FPS. But here in YoloV4, we have to keep the FPS in real time. At the same time, we have to increase the accuracy. So that is why they have adopted many methods, mostly from the training side and the data augmentation side has a lot of effect in the improving the accuracy part. At the same time, there is some improvement from the modules here, from the BoF specials also. While these are the techniques they have finalized and integrated in YoloV4, but they have done lot of ablation studies, lot of evaluations they have done with the different techniques at each and every stage to finalize these are the best for their model, for the model architecture. So if you look at the techniques they have evaluated, you can see that images and backbone different variations are there. They have actually presented their ablation studies in efficient net and CSP ResNet, CSP darknet. These things they have tried, and at the same time SPP, RFB, SAM, all these things, path aggregation network, all these things they have provided ablation studies. And in heads mostly they have actually fixed with YoloV3 only, not much change from the head side. But from the activation functions, they have tried leaky ReLU and swish mesh, all these things. And bounding box aggregation, they have actually experimented with IOU, GIOU, CIOU, all these variations. They finalized DIOU. At the same time, for data augmentation, cutout, mix-up, cut mix, mosaic. So all these things they have tried out. And for regularization, as I mentioned, they have used drop block. But before reaching drop block, they have tried drop path, spatial dropout, all these things. So these are all different methods they have tried out to finalize the things they have used in YoloV4. Right? So this is the complete picture of the techniques they have evaluated so far. So these are from this video. In the next video, we will deep dive into individual modules. So we will deep dive into backbone part, how that architecture idea came up and how the final architecture looks like. At the same time, why SPP is used and how SPP works, and path aggregation network. All these things we will go in detail. And then we will go to the detection head slightly. Detection head is mostly covered in YoloV3 and previous versions already, so we don't go too much into those, but we will go through the bag of freebies and bag of specials, which is one of the major chunk in the YoloV4 paper. So we will go through all of them in the coming videos. Thank you.